before we get to practice problem number 4, let me just walk through this idea of measuring predictive power. So once we have the idea of the correlation coefficient, and really once we have that linear regression equation, we'd like to know just how powerful are the predictions, right? So in that last example, we predicted the number of burglaries for a college with an enrollment of 40,000. We'd like to get an idea just how accurate are those, how trustworthy are those predictions. So there are two ways to do it. One of them is called the residual. So the residual you see there is defined as the difference between an observed value and the value predicted by the regression line. How far apart are they? And we've got a formula there, and I've written it down here. It's on the screen there. E equals y minus y hat. Okay, so remember y is the response variable. So we're thinking, what is the difference between the observed response variable, that would just be collected from some data, it would be given to us in the problem, versus the predicted value of the response variable. That's something that we calculate using the linear regression equation that we get from all of the data together. So let's look at number 4. We're again using the enrollment and burglary data, which is nice. It's already entered in StatCrunch. We don't have to type in a bunch more data. We are going to calculate the residual of the college with an enrollment of 34,000 and has 80 burglaries. So just practice number 4 is just this one part. Can we calculate that residual? So that one is second to last. 34 enrollment, 80 burglaries. What is the residual? So we're going to follow our formula. Okay. The given is what we observed. So we observed that college had 80 burglaries. That's data that we collected. What would have been the predicted? If we had predicted the number of burglaries given their enrollment, what would that have told us? So we're going to use our linear regression equation, just like the way we predicted in that previous problem. So we're going to plug x equals 34 into that equation, just like so. We're going to think of it as equal to y hat, since that's what we're calculating. So same linear regression equation, since it's the same data. Here y hat equals negative 104.120 plus 5.733 times 34. And if you crunch those numbers, I got 90.802. So that is the predicted value. Turns out the regression equation would be a little bit higher than what actually occurred. Probably a good thing in this situation. Okay, well, let's put these numbers into the formula. We're going to take 80, it's always the observed that comes first, minus the predicted, and we get this. E equals negative 10.802. That is the residual. You might ask why we call it by the variable E. Well, residual, I mean, R was already taken. We use that for the correlation coefficient. E stands for error. Like, what's the difference between them, right? How far off are we? Negative 10.802 in this case. So now just below that, back over in the lecture, I defined the residual plot. The residual plot is a graph of all of the residual values from the sample data. So imagine if we went through all 10 of those colleges and did the residuals for each one, and then we plotted those. We'd call that the residual plot. So if you make that a little bit bigger, you can see it for the college we just did. So if you look down, find where about 34 is on the enrollment, and go up, and it's that dot. It's a little bit below the line. There's a line there at 0, so we can see just how far negative we are. And so that one's at negative 10.802. A perfect prediction would be when your dot is almost right on that 0 line. That would be 0 error. And so we can see, some of the points have a positive residual, some have a negative residual, and that 0 pretty much goes right through the middle. One thing to ask yourself in this context would it be better to have a positive residual given enrollment, that we're talking about enrollment in burglaries, or would it be better to have a negative residual given that we're talking about enrollment in burglaries? And well, the truth is, if we were looking at colleges maybe, and we discovered that the college we were thinking about going to, would we want it to have a positive or negative residual? Well, we would want to have a negative residual. In this case, if we're talking about burglaries, we want the actual value to be below the trend, if you will. So hopefully that makes sense. If you think of the average, like what would it be given all the colleges out there? And we'd want our college to be, I would think, we'd want it to be lower than would be expected. Okay, so that's the residual plot. We're not going to really get any questions on the residual plot. I just want you guys to know what it is, that it exists. Okay, the next page, about the first 2/3 of the page, talks more about the residual plot and what would be a good one to see, and then some couple images below of what we're not looking for, what would be bad in a residual plot. I'm going to let you guys read that. Again, we're not going to test you guys on residual plots, but know they exist, and if you need to take more statistics later on, you might really benefit from just reading that little bit, get a little bit more info there. I'm going to skip down to the coefficient of determination, and we'll look at this. So this is the other way to determine how good are your predictions. This is going to be kind of a similar idea to the correlation coefficient. So this is a number that we calculate. The coefficient of determination, it turns out it's going to be a percentage, and it describes how much about y is known given x, and it's denoted as capital R squared. And you see the formula there for it. Capital R squared equals, yeah, we want that negative. I didn't realize I had another note there. I'm just going to switch the page. Capital R squared equals little r squared multiplied by 100%. Okay. There's that formula. Couple things about that. Well, it's a percentage, so the value of capital R squared always going to fall between 0 and 100. The closer you get to the 100, then the more predictive power we say that the variable x has on the variable y. The closer to 0, then the less predictive power. So we like to see those high percentages for the coefficient of determination. On the next page at the top, you see a breakdown of the strength levels, kind of similar to the coefficient of determination, broken up a little bit differently. So what is poor, fair, good, and excellent? Okay. And then we see the statement we might use to interpret the percentage we find. And, again, feels similar to what we saw earlier. Blank percent of the variability in the y variable can be explained by the x variable. Okay, hey, let's check out number 5. What do you know? It's that college burglary data again. Hey, I'm glad we don't have to do this for all sorts of different data, right? So we're going to calculate the coefficient of determination for that college burglary data. So what we would do if this was a fresh problem, what we need is that value of little r. If we can get little r, we can square it, we can multiply it by 100, and that's all we got to do. So if this was a new problem, then we'd enter that data into StatCrunch and go and calculate the correlation coefficient. But we've already done that, and we found it to be 0.888. So we're just going to plug that right on in. Capital R squared equals 0.888 squared times 100%. Okay, one thing I need to mention, the percent That's just like a unit that's going to carry into the answer. So just take point in your calculator, just take 0.888 squared and multiply it by 100. And then that percent sign's just going to carry along. So my camera is just trying to focus here. Okay, so in this case, hopefully you got the same thing that I did. Capital R squared equals 78.854% when we round that to 3 decimal places. Okay. Oh, and state the interpretation as well. Okay, so we'll use that sentence structure just above. We'll go ahead and fill it in. We'll fill in our percentage. 78.854% of the variability in burglaries, here we put the Y variable first, can be explained by enrollment. Now, in this case, it is very important to get the order right here. We want the Y value can be explained by the X variable. So this is the explanatory variable, so it can be explained by that, and that's the response to it. What does that mean exactly? What does that tell us about predictive power? 78.854%. Well, for one, I'd say that's quite high for a percentage. We're almost into the excellent category. We're in the good, or maybe you can say like very good, up at almost 79%. So what we're saying is, if you're trying to make predictions about the burglaries, what you primarily need to know is the enrollment. The enrollment explains 78.854% of the number of burglaries you have. Which kind of causes you to think, well, then what would make up the other 21 point something percent? And you think, well, if we're talking about burglaries, what other factors are involved? And you think, well, what is the campus security like? Just what's the nature of the students who go here, right? Some students are going to be more prone to commit burglaries than others, or be vulnerable to burglaries, something like that. There's just lots of other, what are the dorms like? Are they these old buildings that are easy to break into? Who knows? But I would say, yeah, just knowing enrollment, that is almost all you need, honestly. You're doing pretty well with that. Okay, let's stop this video here. We just have 2 practice problems left, and they'll go well together to wrap things up. See you there.